Okay, wonderful. So if you're watching the recording of this, there's going to be some graphing by hand homework that I'm going to be assigning Monday for 3.2. So today we're going to talk about 3.1, which is graphing quadratic functions, and then we'll probably just kind of get into 3.2, talking about what polynomial functions are and some of their properties. And we'll finish 3.2 next time. Before we get started, does anyone have questions? Okay. Well, wonderful. Okay. Also, I wanted to mention, I noticed that you guys are really dropping off on the homework, and that concerns me, because if you're not doing the homework, then I don't see how you're going to do very well in the class. I don't know why we're not doing the homework, but it's important to be doing that every day to practice so that we can make sure that we're learning and having questions, figuring out what questions we have. It's much easier to watch me do it and say, oh yeah, I get this, it's fine. It's a different story when you have to practice it on your own. So it's really important that we do that homework. So please get working on your homework. All right, 3.1 is about quadratic functions. I'll make this a little bit bigger. All right, so the characteristics of parabolas, and we're going to talk about the characteristics, and we're going to use the characteristics to graph, are listed below. Now, a quadratic function, I'm writing it right now in this form, f of x equals a times x minus h, quantity squared, plus k, where a is not equal to 0. Before we talked about quadratic functions being written in general form, where you had f of x equals ax squared plus bx plus c. We will use that again later on in this section, but for now we're focusing on this standard form of the function so that we can really take some information out of that standard form and use it to graph the function. So we're going to do this 2 different ways. So given the standard form, the graph f is a parabola whose vertex is the point hk. So your vertex, and it's listed down here again, is hk. Be aware that what's in front of the h is a minus sign. So if you have a function that's something like x plus h, like x plus 3 or something, you're going to have to take the opposite of that value to get h. We are going to go through that, so you'll see what I mean. And then k just keeps the sign that's in front of it. So the x coordinate of the vertex takes the opposite sign. A parabola is symmetric with respect to the line x equals h. So we're going to have this vertical line that goes through our parabola. It's not really on the graph, but it's going to represent where we have that symmetry over the parabola, such that if we folded it in half, we'd get that same image to come back. If a is positive, the parabola opens upward. If a is negative, the parabola opens downward. So you're going to be asked on all of these questions almost, does the parabola open up or down? And if you're going to graph it, you need to know that. So the big piece of information here, one of the major things you're going to look at is the sign that's in front of this factor. And it could be that a is 1 and you don't even see it written. If it's positive 1, great, a opens up. But if it's just a negative sign, it's -1, then your graph is going to open down. So that's a big piece of information there. So to graph our parabolas, we are going to determine first whether the parabola opens up or down. That's a really good starting point. We're going to write it down, opens up or opens down, whichever it is, so that we know for when we go to graph it. We're going to determine the vertex of the parabola. As stated previously, the vertex is hk. That's a really important conclusion. I'm going to highlight it in my notes so it sticks out. Very important. The vertex is hk. I don't want later on for you guys to be like, where did you get that? It's right here. Find any x-intercepts by solving f of x equals 0. Remember to find the x-intercept, we let y be 0. Y and f of x will be synonymous in this case. The function's real zeros are the x-intercepts. Find the y-intercept by computing f of 0. And then we're going to plot the intercepts, the vertex, and additional points if we need them. And we'll connect the points with a smooth curve that's shaped like a bowl or an inverted bowl. I sometimes will call it a U shape, even though, I mean, it's not really a U shape, but it's not a V shape either. So it's shaped like a bowl. You guys graphed quadratic functions when we were talking about transformations of functions in 2.5, and you graphed the standard parabola like y equals x squared, and then you shifted it around and reflected it and did all sorts of things to it. So now instead of talking about just applying straight up transformations, which you will actually see here, we're going to be looking at these in a different type of form. And if you don't see it in this form, we're going to put it in this form. So that's going to be part of our exercise here, is using that idea of completing the square that we learned in 1.5 to switch our equations so that they're written in standard form. So for number 1, write the equation as a quadratic function written in standard form. And then we're going to analyze the function and graph it. So the first thing we're going to do is write it in standard form. If you are asked to do that first, and then you'll get all of the information from that starting point. So that means what I want to have is f of x equals a times x minus h squared plus k. Right now I have y minus 4 equals x minus 1 quantity squared, but we're really close to getting it in standard form. In this case, if I want to write it in standard form, I can just take this 4 and add it on both sides of the function. And when I do that, now I have y equals x minus 1 squared plus 4. And now we are in standard form. Now, we didn't have to do a whole lot to that one. You're going to come across some of these where you're given something completely different, where you don't have a quantity that's being squared. And you're going to have to do a little bit more work. But this is what standard form looks like. If for whatever reason you want to have it in f of x notation, that's fine. It does not matter to me. Now, officially, yes, you could technically use your transformations to graph this parabola and then you'd be done. But we're going to be answering all these questions and then kind of pulling this all together. So let's go ahead and answer the questions and then we'll graph the function. Write the equation as a function in standard form. We already did that, where we had a little more space up top. B, does the parabola open up or down? So in order to answer this question, you're going to look at the coefficient in front of your squared term. In this case, you just have x minus 1 quantity squared. That means that the coefficient a is actually equal to positive 1. It's not written, so you can assume it's positive 1. Oh, sorry, Angel. You know, I don't think there was too much to write above that, actually. Oh, you didn't get the notes because of your address change. Got it. Is that good? Can we do that? Okay. So if we can say that a equals 1, in this case, we can then say that the parabola opens up. And just like that, we already have a good deal of information about this graph. The next thing we're going to do is find the vertex. The vertex is HK. Now remember that H is whatever follows the minus sign. If you would like, you can even parallel the original standard form equation with H and K in it underneath here so you can see what H and K have to be. In the place of K is 4, and in the place of H is 1. So don't say that your vertex is at -1, 4. That's not the case. H is whatever follows that minus sign. If you had a plus, you would have to take the opposite sign. But since an H follows the minus sign and a 1 follows the minus sign, that's what you're going to use here. So for find the vertex, we're going to say that our vertex is HK. And in this case, H would have to be 1, K would have to be 4. Okay. Are there questions so far? Wonderful. The vertex, why not -1? People always want to know that. So I know it's really hard for us to look at this as being a -1 and not think of it as -1. You have to remember that the x-coordinate of the vertex, I'll even write a note about it. The x-coordinate of the vertex is the value that follows the minus sign in x minus h squared. So whatever value follows the minus sign, that's what your x-coordinate of the vertex is going to be, or that's what h is going to be. So in this case, you're literally just swapping them out. You're saying, okay, x minus h, it's not negative h that's the x-coordinate of the vertex, it's positive h. So whatever follows that minus sign is going to be the x-coordinate of your vertex. If it was a plus sign, then you could switch that to like x minus -1. If it was x plus 1, you could do it that way. I think we will have an example with that. Does that help, Ben? Or are you still thinking that that's weird? Good, okay. Did anyone else have a question about the coordinates of the vertex? Okay, that does get missed quite a bit, just because we see a minus and we think negative. Okay, so the vertex is at 1, 4. To find the x-intercepts, we're going to let y equal 0 every time. Sorry, the ice cream truck is here and everyone's going completely berserk. All right, to find the x-intercepts, we solve for f of x equals 0. If you want to call it y equals 0, fine, doesn't matter. Whenever you're finding x-intercepts, you're letting y equal 0. So go ahead and go back to your function. And we're saying now 0 is equal to x minus 1 squared plus 4. And what we're doing here is we're letting y be 0, because if y is 0, then we have to be sitting on the x-axis. I'm looking for x-intercepts. That means I'm looking for values that lie somewhere on this x-axis. If that's the case, then the y value has to be 0. That's why we're letting the y value be 0. And we're going to solve for x to see where x exists when y is 0. Now notice that when you do this, you end up in a pickle because you have -4 equals some quantity that's being squared. Well, when you take a plus or minus on the left-hand side, I guess I'll do it on the left-hand side to get x minus 1 by itself, then you end up with plus or minus the square root of -4. Now, if I asked you to just solve the equation, that would be fine. You could solve it and you would get plus or minus 2i equals x minus 1. However, this is not a point that you can say lies on your graph. If I asked you to find me an x-intercept and you said, well, it exists at 1 plus or minus 2i, okay, where would you graph it? It doesn't exist on your graph because it's an imaginary number. You can't graph it. So in this case, you would say that this graph has no x-intercepts. And that's because these values are imaginary. Now, sometimes I see students immediately plot the vertex, and they would say, okay, well, if the vertex is at 1, 4, and remember the vertex of a parabola is that place where it either bottoms out or hits its max. So they would say, okay, if the vertex is at 1, 4 and the parabola opens up, there's no way it can have any x-intercepts. And in that case, you don't even need to show me the work because there's nothing to show if you at least have that down and you can explain how you arrived at that conclusion. So that's fine. If you plot the vertex and say, well, it opens up, there's no way it could possibly hit the x-axis, I understand. That makes sense. Questions about the x-intercepts? Now we'll find the y-intercept. To find the y-intercept, we're going to let x equals 0. For the same reasoning, if I'm looking for the y-intercept, I'm trying to find where does the graph intersect this axis. And the only place that can occur would be at some value where x is 0. It means I'm moving nowhere to the left or to the right. So if that's the case, I'm going to go ahead and take my function. I'm trying to solve for a y-intercept. You can still call it f of x if you want, whatever you want to do there. I'm going to let x equal 0. And I'm going to solve for y. So I'm just using the function, substituting 0 for x, and solving. So 0 minus 1 is -1. -1 squared is +1. +1 plus 4 is 5. So that means that your y-intercept is at 0, 5. Now, next time we go over one of these on the next page, we might start to build this as we go along, because then if you get some sort of result that doesn't make sense, you can think, wait a second, something is off. I need to check what it is. For now, I just want to focus on finding all this information. All right, the axis of symmetry was also given to you up here in the directions somewhere. Oh, maybe it wasn't. It was stated that the axis of symmetry is a line that goes through x equals h. Oh, well, I guess it kind of says it here. X equals h is where your parabola is symmetric about that line. So your axis of symmetry is just always going to be written in the form of an equation. It is the equation of a line. And it's just going to be whatever the x coordinate of your vertex is. So here we have a vertex at 1, 4. That means that the axis of symmetry is x equals 1. And that's because our axis of symmetry is always at x equals h. Now, as for the domain and range, we focused on finding the domain and range for quadratic functions in the last chapter. You're looking at this function, and it's a quadratic. It's any sort of polynomial function. It's going to have a domain of all real numbers. But for the domain, you're just looking, is there any value of x that would violate the domain? And you wouldn't be able to find one. You don't have any variables in the denominator, and you don't have any radicals for which you could be taking the square root of a negative number. So the domain of our function is going to go from negative to positive infinity. Now, if you'd like to graph the function before finding the range, you'd probably find that easier to do. You don't have to, but I usually would graph it first and then find the range. So let's go ahead and start to graph this function. I know I'm going to start with the vertex, which is at 1, 4. So 1, 2, 3, 4. There's my vertex right there. I know my parabola opens up. So my goal now is to try to find other points that I can plot without having to find a bunch of different values. I know, for instance, that I have a y-intercept at 0, 5. So we're going to go ahead and plot the y-intercept at 0, 5. Now, I can use the fact that my parabola has symmetry to graph that similar point on the other side of the parabola. So what I'm going to do now is I'm going to represent this axis of symmetry with a dotted line. I don't want to make it solid because I don't want to have it actually appear as though it's part of my graph. But I'm just going to make my axis of symmetry this dotted or dashed line that goes through x equals 1. And that's my axis of symmetry. I usually just call that AOS. And because I have that axis of symmetry, I can mirror my function over to the other side of that. So I had a point at 0, 5. Well, now I can say I have a point that's reflected over that line, not at 0, 5, but at 2, 5, because my parabola has to be symmetric about that line. Now, this is probably enough to get you a pretty decent picture. If you feel like you want one more point because you're kind of like, I don't know if I really know exactly what's happening here. I mean, parabolas all kind of behave in the same way. This is a pretty good starting point. I would probably just get one more point on this graph just by using a table of values. For instance, I don't have any other points here I can graph. I don't have any x-intercepts, but I can think about what might possibly happen as I go to the left of this point. So maybe looking at what happens when x equals -1. And in order to determine that, and I'm just going to put this somewhere, just I don't need a ton of space, but a little bit. I'm going to figure out when x equals -1, not +1. When x equals -1, what is y? Just so I can get one more point so I can have a really nice shape to the graph, and then I can go ahead and finish graphing it. And of course, if I look at what happens at x equals -1, I'm going to have the same value for y equals, or I'm sorry, for x equals 3. Their y values will be the same by symmetry. So let's go ahead and use our original function. I'm going to find f of -1. So for x, I'm going to substitute -1 into my function. So -1 minus 1, quantity squared, plus 4, and then I'll get that corresponding y value for the function. So -2 squared plus 4. -2 times -2 is +4, plus 4 is 8. So that means that I should have a point on my graph at -1, 8. Now, you'll graph it and you'll know something is wrong if it does not look like a parabola. So you should have a point here that it keeps increasing a little bit more quickly, but it shouldn't be a point that's down here somewhere. That wouldn't make any sense. So at -1, 8, I have this point. I'll label that so everyone can see it. And by symmetry, I can say that I also have a point then at 3, 8. And that's it. 5 points will make a really nice parabola. Connect them with a nice smooth curve. Try not to make it look totally vertical. It should be going off to the side, but it's going to do that pretty quickly. Put some arrows on the ends of your curve so it looks like it's still continuing on its course. Does anyone have a question about the graph before we answer that last question about the range? Okay. Wonderful. All right, so to find the range of the function, we can look at the graph, and we see that the smallest y value for which our parabola is graphed is y equals -4. That is on the graph, so we can, or I'm sorry, did I say -4? I meant +4. That is on the graph, so we're going to go from 4 all the way up to infinity. Remember, we can never equal infinity, so we're always going to put an open parenthesis on infinity. And that is how we analyze and graph a quadratic function. And you could always check this with your transformations. That's a little bit harder to do once you start doing reflections and stretching and shrinking. But looking, for instance, at this function, you know it's your standard parabola shifted to the right 1 unit and up 4 units. And sure enough, you see it's shifted to the right 1 unit and up 4 units. Okay. Any questions on this parabola before we do another one? We'll go through the next one a little faster. Okay. Okay, now your next page has a bunch of instructions on the top. And I was curious, where did those come from? And it's because I forgot to remove them. The same exact instructions are on the next page for the problem that we get to there. So we're gonna ignore these for now, and we're gonna use those instructions when we come to them on the next page. This one we're gonna do just like we did the last problem. Here's the big difference. The last problem was almost in standard form already. This one is nowhere even close. In the last problem, you already had it so that you had a quantity that was being squared. You don't have a sum or difference being squared here. So we are going to have to complete the square in order to write this in standard form. So let's do that now. Now, I would suggest changing f of x to y when you do this. You don't have to, but I would suggest it. It'll make it a little bit easier to work with. Now, you guys are not used to completing the square with a y here. When we were completing the square to solve equations in 1.5, you had a constant on this side. You didn't have this extra y. So the process will be very similar with just a slight difference. We still want to bring this constant over to the other side, just like we did when we were solving equations by completing the square. So we're going to go ahead and add 7 on both sides. So you're going to have y plus 7 equals x squared plus 6x. Now, whatever you do, resist the urge to factor out an x here. You don't want to do that. You're trying to create a perfect square trinomial. So don't factor on the right-hand side. What we're going to do now is we're going to create that perfect square trinomial on the right-hand side, and whatever value we need to add to the right-hand side, we're also going to add to the left-hand side. So let's go ahead and take half of the middle term and square it. So 6 divided by 2 squared is 3 squared, which is 9. And that's the quantity that we're going to add to both sides. On the left-hand side, I have y plus 7 plus 9. If you want to go ahead and compute that sum, be my guest. I'm just wanting to make sure it's all written out so nothing looks confusing. Equals x squared plus 6x plus 9. Now we're going to simplify on the left, and on the right, we're going to go ahead and factor. So to factor our perfect square trinomial, remember we keep the variable to the first power, then we keep the sign that's in front of the middle term, and we take half of the middle term's coefficient, and we square it. And now we're almost done. To get this in standard form, what I'm trying to get to is this, f of x equals a times x minus h squared plus k. I'm really close because I can see already that a is going to be 1. I have a quantity that's being squared, a binomial squared, and then I'm going to add that k to it. So I'm going to change y back to f of x, and I'm going to subtract 16 on both sides. And now we have standard form. F of x equals a times x minus h squared plus k. Does anyone have a question about how we got this quadratic function into standard form?
I have a question. Why did you change it back to f of x instead of keeping it at y?
You don't have to. I just mostly did it as a formality in this case because a lot of your directions are, like solve f of x equals 0. And standard form was written as f of x equals. On a test, if I said write this in standard form, if you put y, I would just be thrilled that you got the right-hand side correct. So I mostly did it as a formality.
Okay.
Yeah. Any other questions on finding the standard form for this quadratic function? By the way, this is so useful. I hope that you folks don't get to the end of this and then say, well, I hope I never have to do this again, because it's such a useful skill. I use this in calc all the time because sometimes you get these quadratic functions that are just much faster to graph if you just write them in this form. You write them in this form and you know you're just taking your standard parabola and you're shifting it left 3 units and down 16 units. That's it. Life is so much easier when you get it into this form. Over here, we have other ways of working on it in this form. I don't know. Personally, I love this. I use it all the time. And when you're trying to quickly graph functions in calc, I think you'll find this to be an incredibly useful tool, I hope. So don't think of this as some unnecessary hoop you have to jump through. It's a really fantastic, useful tool for graphing quadratic functions. Okay. Now, all right, so A we already did. Oh yeah, I did the work up there, but okay, we'll put it down here. F of x equals the quantity x plus 3 squared minus 16. Wonderful. Now, the second question is, does the parabola open up or down? Well, again, you're looking at the factor that's in front of your parentheses, and you don't see anything. That doesn't mean A is 0, that means A is 1. And you don't see a negative sign, so it must be positive 1. So that means A is 1, and your parabola opens up. Now we're going to find the vertex. So this is going to bring us back to Ben's question from earlier of making sure we get that sign correct when we're taking out that x coordinate value. All right, watch what I'm going to do here. Right now I have x plus 3 squared minus 16. But remember, the standard form for your quadratic function looked more like, let's see if I can get on, there it is, x minus h squared plus k. So what I'm going to do is I'm going to turn this into a form that looks like that. Instead of calling it x plus 3, I'm going to call this x minus negative 3. And I'm going to write our standard form function below this one so you can compare. So that is your standard form. Remember, your vertex is HK. You don't have to do this when you're working on your exams, but I think you'll get used to just taking the opposite of the sign for this term. But you can always rewrite it like this if you're not sure. H is whatever is behind this minus sign. And in our case, what's behind the minus sign is negative 3. So when we're finding our vertex, we're going to write this as negative 3. And then K, maybe I should have taken this one step further. And instead of calling it minus 16, I could have called it plus negative 16. Then you can see how K would very easily just kind of take the spot of negative 16. So to recap with the vertex, if you have a plus sign in this x term, or no matter what sign it is, just take the opposite. So h is always just going to be the opposite of whatever that term sign is. K is going to keep whatever sign is in front of it. So your vertex is hk, which is negative 3, negative 16. Any questions on the vertex? I know it seems like a really small thing, but it is really important. Everything is based off of making sure you have the correct signs there. All right, let's find the x-intercepts. To find the x-intercepts, we're going to let y equal 0, or let f of x be 0, whichever way you want to think about it. So I'm going to go ahead and take my function. I'm going to swap out 0 for f of x, and then I'm going to solve for x. So I have x plus 3 quantity squared minus 16 is equal to 0. And you can solve this by using the square root property. I have seen students expand this out by foiling and then subtract 16 and then use the quadratic formula. That's a lot of work. Just use the square root property. That's why you learned it. Add 16 on both sides. And then take the square root of both sides. When you take the square root, make sure you use a plus or minus sign. And now you have plus or minus 4 on the left. And then you can go ahead and subtract 3 from both sides. Now, this is a situation where you already have a simplified value. So you're going to have 2 values that need to each be simplified. So you are going to have x equals negative 3 plus 4 and x equals negative 3 minus 4. That means x equals 1 and x equals negative 7. And remember that these are x-intercepts. They are points on your graph. They exist at 1, 0 and negative 7, 0. Now, my suggestion would be at this point, to make sure that you're not using bad work, you might want to start plotting this on your graph. I would probably go ahead and plot the vertex at negative 3, negative 16. Did I really not? Oh, yeah. You know, this was probably one of those notes to self where I told myself, oh, fix this, and then I somehow ended up not seeing the note later on. So let's see, this goes to 8. I'm trying to get to negative 16. It's got to be somewhere like down there. Sorry about that, guys. Okay, so negative 3, negative 16 is right around here. And we have x-intercepts at 1, 0 and negative 7, 0. Now, it's a little bit harder to eyeball in this instance, but notice that negative 3 is smack in between 1 and negative 7. So when you're at negative 7, you move to the right 4 units and you get to negative 3. Move to the right 4 more units and you get to 1. So it's very promising that our x-intercepts are equidistant from the axis of symmetry. So at that point, I would say, yep, it looks like everything so far is good. Go ahead and plot your axis of symmetry. At x equals negative 3. Now we do have to find the y-intercept, but f is find the axis of symmetry. We just plotted it and we said it was at x equals negative 3. X equals h. Since x equals h, x equals negative 3. So this is what we have so far. Any questions so far? I kind of like these problems just because it's like multi-part, you know, you kind of know where you're going because it keeps telling you what to do and then you're just kind of filling in the pieces. Let's go back to E, which is find the y-intercept. To find the y-intercept, we are going to let x equal 0. So going back to our function, which I completely mangled here. Oh, actually, it's right there, so we're good to go. I'm gonna, let's use y. We're trying to find the y-intercept. 0 plus 3 quantity squared minus 16. And then we'll simplify. 3 squared is 9, and then minus 16 is negative 7. And this is actually looking really good because that makes sense to me that our x-intercept would be negative 7. If you ended up getting an x-intercept that was something like, or I'm sorry, a y-intercept that was something like positive 7, alarm bells should be going off for you in that instance. If your y-intercept was +7, that would not make any sense because your parabola can't go down and then go up and then cross back over again. It wouldn't be a function. It's not going to happen. So anytime you get bizarre data like that, you're going to have to go back and check which part of your work was wrong. And sometimes it is in these multi-step problems, it can be kind of hard to isolate the issue. But having an or a y-intercept at -7 makes all the sense in the world. It's perfect, actually. There's your y-intercept. And go ahead and use the axis of symmetry to plot one more point where y is -7. And you can do that. You're noticing here that the axis of symmetry is at x equals -3. That means that the axis of symmetry is 3 units away from the y-axis. So go 3 units in the other direction to -6. And you can plot a point there at -6, -7. And that's by symmetry. And really at this point, even though we have to still find the domain and range, we have 5 solid points for our parabola. Go ahead and connect them with a nice smooth curve. Let's see, I'm just going to start here and then I'll carry it back up again. Notice that my lines or my curves don't all of a sudden jut out this way. I've seen a lot of students who start to make their parabolas and then they'll go whoop, like that and make them go like back down again. It's weird. You should be seeing this situation where the behavior of your graph is still just going to continue on this type of movement. It's not going to all of a sudden run off to the side and do crazy things. So this is what it should look like. Now the domain of any quadratic function is all real numbers. The range, because our graph opens up, we're going to have our smallest point at the y-coordinate of the vertex, which is at -16. So our range is going to start at -16 and go all the way up to +infinity. It's a dog again. Oh, whoops. There you go. Okay, questions on this one? Okay. Moving on. Those instructions we ignored last time, we're going to use now. Determine whether the parabola opens upward or downward. If A is positive, it opens upward. If A is negative, it opens downward. But what we're doing here is instead of looking at the quadratic function in standard form, we're going to look at it in the form f of x equals ax squared plus bx plus c. Now, I have a note here because I don't want to forget to do it. For practice, we are going to write it in standard form, but I do want to use these instructions. So I think what we're going to do is we're going to go through and graph it using this set of instructions, and then for extra practice, for good measure, I want us to go ahead and write the standard form equation because it's a little bit of a different process since this function starts with a negative. Okay, so we're going to look at A to determine the opening of the graph. Then we're going to determine the vertex of the parabola. Now we're going to do this using a formula. In this case, the x-coordinate of the vertex is -b over 2a. The y-coordinate of the vertex is the function value at -b over 2a. So what you're going to do is you're going to find -b over 2a using the coefficients for a and b that are given to you in the function. Once you determine what that number is for -b over 2a, you're going to evaluate the function at that number. And that's going to give you the y-coordinate of the vertex. Now, once you have the vertex and the opening, you have a lot of information. But from there, you're going to try to find a few more points to put on your graph, like an two x-intercepts, hopefully. Maybe a y-intercept. You will be able to find a y-intercept regardless. And then we're going to see if we need any additional points. If not, we'll just take the points that we have and connect them with a nice smooth curve. So that's what we're going to do. Let's go ahead. Now you have number 3, f of x equals negative x squared minus 4x plus 1. And we're going to go ahead and take our function and analyze it and graph it. I want to do this last because I think it's important, but I want to focus on using this method. Now, by the way, if you're like, wait a second, didn't we just do this using standard form? Why are we doing this now? Because there are multiple ways of doing the same thing. And it's good to know both. Some of you will prefer this way. Others are going to prefer the way that we did this on the first two. I prefer this way. I find that students like this better. I'm going to ask you, though, on your exam to do it in a particular way. So you got to know how to do both. I'll probably ask you how to do the whole process using standard form. And then I might ask you to just find the vertex using this form. Something like that. We'll see. I haven't written the test yet, obviously. Okay, does the parabola open up or down is what part A is asking. Now, all we have to do here is look at the sign in front of the lead term. So A is whatever the coefficient is on x squared. In this case, x squared has a coefficient of -1. So we can say that A equals -1. So we know that our parabola must open downward. If A is negative, the parabola opens down. All right, so that's one important thing that we just found. The next thing we're going to do is find the vertex, and we're going to use our new formula in order to do that. So we're going to take negative b over 2a. Now, negative b would be -4. B is already -4, so be careful here. Don't use the negative sign that's already on there and say we've got it covered. No, you're taking negative of whatever that coefficient is. And then over 2a, and in this case, a is -1. And then we'll simplify. This gives you +4 over -2, which is equal to -2. Now this is the x-coordinate of the vertex. To find the y-coordinate of the vertex, we're going to find f of -2. So whatever this value is, to find the y-coordinate, you're going to evaluate the function at this value. So f of -b over 2a is equal to f of -2. So you're going to take your function up here and evaluate it at -2. Don't forget there's a negative in front of it. So you'll have negative and then -2 squared minus 4 times -2 plus 1, and you'll simplify. -2 squared is -2 times -2, which is +4, but there's still a negative sign in front of that term. So you have +4 plus 8 plus 1. Did I say +4? Sorry, -4. Sorry, losing it here. -4 plus 8 plus 1 is +4 plus 1, which is 5. That is the y-coordinate of your vertex. So now you can go ahead and conclude that the vertex is at -2, 5. Put a box around that. If you want to go ahead and plot the vertex, feel free. If you want to wait until you have some intercepts, you can do that too. Sometimes I just like to put the vertex on there. So -2, 5 is right there. And you know that your parabola is opening downward. So you are expecting to have some x-intercepts here. If it opens down, it's going to have to eventually cross the x-axis. Okay, now to find the x-intercepts, let y equal 0. So you'll have 0 equals -x² minus 4x plus 1. You're going to have to use the quadratic formula here. You guys find the x-intercepts. I'm going to move my lamp back over here because it's so dark. Okay, now, if you've used the quadratic formula, you came up with this. Now, if I was asking you to just solve the equation and simplify, this would not be simplified. However, a lot of times when we're graphing, it doesn't make sense to leave our answer in exact form. And I tell you guys all the time, leave your answers exact, leave them exact. But when you're graphing, how are you going to know where to plot the point if you don't have a decimal approximation for that value? So feel free to simplify it further if you really want to. What really matters is that you have some clue as to where to put these points, since we need to graph them. Now, I think my math lab is going to ask you to approximate these. If not, remember that to simplify, you have to split this quantity up into 2 perfect square factors and then simplify it. So in case my math lab really wants you to simplify this, you have these 2 values at -2 plus or minus the square root of 5. But you don't know where to graph those if you don't pop them into your calculator and get some sort of decimal approximations. So do that real quick. Oh, Here, you know how to enter this in your calculator. Okay, so -2 plus the square root of 5 is approximately equal to 0.236. You're only going to get to about 0.2 accuracy at most when you plot this, so you don't need to put in a bunch of decimal places there. If my math lab asks you for an approximation, which I bet it will, they're going to specify a number of decimal places. -2 minus the square root of 5 is approximately -4.236. So these are your x-intercepts. Before I proceed, does anyone have a question about the x-intercepts or what to do with them? I'll find them, I should have said. Okay. So let's plot them and make sure they make sense to our graph. Approximately 0.236 is, right around that 1/4 mark. And it opens downward. You already know your parabola opens down. So this looks pretty good. And then approximately -4¼ is about here. And that looks pretty good too. If you'd like to pop your axis of symmetry on there right now, it's probably a good idea, but you should be able to see that these x-intercepts appear to be pretty much equidistant from that axis of symmetry, and that's the important thing. So those are your x-intercepts. Now the y-intercept, by the way, it's good if you have some sort of idea of where you expect this point to be. If you know that your parabola opens down, you know it's coming through this way. This point right here is on the other side of the y-axis, so it must be the case that the y-intercept is somewhere up here, maybe even at 1, somewhere over here. Maybe not quite at 1, but we're going to see. So you have an idea of where you're expecting it to be. So let's go ahead and find the y-intercept by finding f of 0. Let x equal 0 to find the y-intercept. And f of 0 is easiest to compute if you look at your function in this form, because that means the first and second terms go to 0, and all you're left with is +1. So f of 0 equals 1, which is, when we eyeballed it, just about where it looked like it was supposed to be. So we'll go ahead and plot that y-intercept here at 0, 1. And then you can use your axis of symmetry to go 2 units left of the axis of symmetry and get one more point by symmetry at -4, 1. We do still have to find the domain and range, but let's go ahead and connect these points with a nice parabolic curve. Something like this. It's beautiful. Your parabolas should look like this. Nothing crazy that doesn't look like this. It should always have this shape. I'm always shocked when I'm grading parabolas on exams and they look so crazy. This is what they should look like. All right, we still have to answer this question about our axis of symmetry for E. You know, maybe because these are multi-parters, it might help if I zoom back out a little bit. Find the axis of symmetry. Well, that occurs at the x-coordinate of the vertex, which was -2. So our axis of symmetry we drew at x equals -2. We can go ahead and label it here also. And then we'll find the domain and range. It's a parabola. The domain will be all real numbers. The range this time, however, is going to look a little bit different because of the fact that the graph opened downward. The lowest y value you can find on the graph, you can't actually find because this graph is going to go all the way down to -infinity. But when it goes up, it's not going to go up to -infinity. It only can go up as far as this vertex, which is at y equals 5. And once it hits this point at 5, it heads back down again. That means that 5 is the highest point we can actually attain on the graph. So to find the range, we're going to go from -infinity up to 5. Oh, I love this chapter. It's so fun. I really love this chapter. I'm not kidding. I actually love this stuff. I mean, it's awesome how you don't even need your graphing calculator. You're just using all the information algebraically to put things together. Oh, I forgot that I promised you we were going to write the function in standard form. before I do that, does anyone have a question about this parabola, how we graphed it, or any of the pieces that we used to graph it? Okay, I can only see 2 of you, so if anyone has a question, you're going to have to tell me. All right, so for practice, let's write this function in standard form. Go ahead and change f of x to y. Now, anytime we're solving by completing the square or completing the square, we want to move that constant to the other side. So subtract 1 on both sides. You have y minus 1 equals negative x squared minus 4x. Okay, now, when you're taking half of your middle coefficient and squaring it, you can't use it right now because you have to have a coefficient of x squared as 1. Remember, one of the steps we went through was we divided every term by the coefficient of x squared. Well, in this case, the coefficient of x squared is actually negative 1. I'm having an issue with my focus here. I want to make sure it does what it's supposed to do. Every time I threaten to autofocus it, it fixes itself. So instead of going through and dividing every term by this negative, because we don't want to do that in this case because of our variable y, what we're going to do is we're just going to move it off to the side. We're going to factor it out, and we're going to work on what's inside the parentheses. So whenever we're completing the square and trying to find these quadratic functions in standard form, if there's a lead coefficient other than 1, factor it out and then work inside the parentheses. So that means if I want to complete the square inside the parentheses, I need to look at the number 4 and take half of 4 and square it. So I'm going to take 4 over 2 and square it. 2 squared is also 4. Now we need to be really careful here again, because I don't want to say add 4 to both sides. I do want to add 4 inside the parentheses, but it's going to look a little bit different on the left. I've created this perfect square trinomial now inside the parentheses. The issue is I didn't actually add 4 to this side. I added 4 inside the parentheses. I actually added negative 4 because this negative sign is going to end up getting distributed into all of these terms. So when we add to both sides, in our case, we have to actually add negative 4. Okay, that's because of the fact that we have this negative on the outside. So officially it's not 4, it is negative 4. Now we'll simplify. On the left we have y minus 5 equals negative, and then we'll complete the square, x plus 2 squared. And then to get this into a standard form notation, just add 5 on both sides. And if you want to change the y to f of x, that would be fine, but you don't have to. I will, just to make it official. Now notice that if you were trying to find the vertex hk, you're taking the opposite of whatever sign is in this x term. So your vertex would be negative 2 and then you're keeping the sign that's on k, positive 5, which is the same exact vertex that you found using our new formula. So it's all just about which way you want to do it and which way you're being asked to do it. Don't solve everything the same way, because on your exam, I am going to ask you to convert something like this into standard form. So if you just say, I want to skip that, and then you just do everything this way, you're going to lose the points for finding all of this information using that standard form function. It's important. We got to figure out how to do that. Completing the square is key in college algebra. Questions on number 3. Okay. The last thing we're going to talk about in 3.1 has to do with minimum and maximum values. You should already have a pretty intuitive feel about this just based off of the work that we did with the range and determining, well, if the function is opening up or down, we're only going to go up or down to the vertex. That's sort of the concept that we're going to be using here. So consider the quadratic function f of x equals ax squared plus bx plus c. If a is greater than 0, then f has a minimum that occurs at x equals negative b over 2a. And remember, if a is greater than 0, that means that your graph opens up. You want to make a note of that. If a is less than 0, f has a minimum that occurs at that x coordinate of the vertex. And this occurs when your graph opens down. So that should make sense. Your graph opens down. You've got this maximum value that's occurring at the vertex. If your graph opens up, then you've got a minimum value that's occurring at the vertex. So the minimum value occurs at the x value of the vertex. The minimum value is whatever that y value is as you go up or down. So that would be the y coordinate of the vertex. So this is really just sort of a subset of what we've already done, but we're going to determine whether the given quadratic function has a minimum or maximum value. Then we'll find the coordinates of the minimum or maximum point. So for number 4, we have f of x equals 2x squared minus 2x minus 3. So first you're going to determine, do we have a minimum or maximum value? You know that a is 2 and 2 is greater than 0. Therefore, it must be the case that your parabola opens up. And a lot of times it just helps to draw a little tiny parabola that opens up, and then you kind of know, okay, if it opens up, it must be the case that we have a minimum value. It's only going to go down so far, but we won't have a maximum value. It's going to keep going up and up and up and up and up forever. So we must have a minimum value. So you're going to be asked questions like this on my math lab. You're going to be asked, does the function have a minimum or a max? And then where does the minimum occur? What is the minimum? So in order to find that, we're going to look at the vertex using the formula. Now, of course, you're more than welcome to take this function and rewrite it using completing the square. And it's going to be a little bit more work, though, just because you have a coefficient of 2 in front of the x squared. You might as well just use the formula when you're just answering basically this one question. So negative b over 2a is negative, the value of b here is negative 2 divided by 2a is 2 over 4, which is 1/2. So that's the x coordinate of the vertex. To find the y coordinate of the vertex, you're going to find f of 1/2. You're going to evaluate the function there. Feel free to use your calculator to do this if you don't like fractions. But you're going to evaluate the function at 1/2 and simplify. 1/2 squared is 1/4. 2 times a fourth is also a half. So you're looking at a half minus 4, which is negative 3.5, which is negative 7/2. So determine whether the quadratic function has a min or max. We did that. Then find the coordinates of the minimum or maximum point. So you're going to say that you have a minimum at 1/2, negative 7/2. Make sure you're following the directions in my math lab. Even though negative 3.5 is exact, every once in a while they're particular about wanting fractions versus decimals. So if it says enter your answer as use a whole number or a fraction or something, using integers or fractions, do this. If it says decimal, fine. Sometimes it'll say use an integer or fraction and it'll still accept the decimal. It's hard to say. If it's terminating, if it's something like 1/3, you cannot just enter that as 0.333. Can't do that. Okay, you guys do the next one. I have to finish my attendance here. Minimum or maximum, and then find what the value is. All right, so let's see. Does anyone want to volunteer? You want to unmute yourselves and tell me if it's a minimum or a maximum? Anyone?
It's a maximum.
It's a, wait, which one is it? No, you're right, maximum, right? Sorry, you like broke up right there for a second. You said maximum, right? Okay, wonderful. Yes, it opens down, a equals -1, which is less than 0. If it opens down, then it is a max. Okay, does anyone else want to unmute themselves and tell me what they got for their coordinate point here, your XY coordinate of the maximum?
I got -1, -6.
-1, -6. Did anyone else get -1, -6?
I got -7.
I got -7 too. Can anyone else? Who said that? I don't know who's.
I got -7.
-7. All right, we'll go through it. The -1 was correct. And the -6 was close. So let's go through it. For your vertex, we're looking at -b over 2a. So -2 over 2 times -1 is 2 over -2, which is -1. And then f of -1 is -1 squared minus, oh, lots of sign issues here that could possibly plague us. So let's see, -1 plus 2 minus 8 is 1 minus 8, which is -7. Excellent. I'm just so glad you guys volunteered. I'm looking into ways, I feel like when I first started this class, I was just mostly focusing on how to properly get the material out. But now I'm really trying to think about how can I make this class more interactive? So I might be sending out a survey to you pretty soon, because that's going to be my next area of focus now that I kind of feel like we have the other stuff down. Because maybe you guys don't want it to be more interactive. I don't know. That's why I want to kind of get an idea for what you would prefer, just to try to make it a little more interactive if possible. Because I like to hear what you have to say. Definitely we have a maximum at -1, -7. Any questions there? My son's kindergarten teacher today at the end of class, they had like 15 minutes and she was like, I want to know how everyone's feeling right now. And she shouldn't have asked, because first of all, my son's like crying on the floor because he feels like he's not getting called on. And I'm like, if she can't see you in your seat because you're on the floor crying, she's not going to ask you. But then this one girl was like, well, I'm feeling really bored because school is really boring and all I do is sit here. And then this other girl was like, I'm feeling really sad because you never call on me and I keep raising my hand and you never call on me. And it was like the saddest thing, these poor kindergartners. And you guys are just kind of like, whatever, like, we're just kind of here. So not the same thing where maybe you don't want to be as interactive, which makes sense, but maybe you do. I don't know. Okay. Mary, the CEO of a manufacturing company, is interested in knowing the number of automobiles that should be manufactured to minimize the cost. This is what a lot of these parabolic problems are leading to, is just being able to find minimum and maximum values, such as cost, or sometimes making like a maximum area. There are people whose entire job is just to optimize spaces, you know, like they're loading things onto pallets, and those pallets are getting loaded onto trucks, and boxes of cereal are made at a particular size just because they need to fit on the truck in just the right way so that that truck can optimize the amount of volume inside of its cabin in the back. So really important here to talk about this concept of optimizing, or optimizing some sort of quantity. The function c of x equals 4x squared plus 32x plus 128 gives the cost in millions of dollars for the company to manufacture x thousand automobiles. Find the number of automobiles that must be produced to minimize the cost. Give the domain and range for the function in interval notation. So in order to talk about minimizing the cost, we need to look at the cost function. So you were given here that the function c of x gives the cost. So that's how we're going to talk about minimizing the cost. And in order to minimize it, we're going to have to figure out where we have this bottoming out point. Clearly the parabola is going to open up because your value of a is positive, but if you're minimizing a quantity, it must be the case that you have to have a situation where your function has a positive value of a. So let's minimize the cost. That just means we're trying to find here on our function c of x, this value such that c of x is the smallest it can possibly be. So where does that occur as far as your x value is concerned? It's over here. Okay, find the number of automobiles that must be produced. And remember, x is a number of thousands of automobiles. So let's go ahead and minimize this quantity by finding the vertex, -b over 2a, and use the quantities that are given. So negative 32 divided by 2 times 4, and you get 4. So find the number of automobiles that must be produced to minimize the cost. Give the domain and range for the function in interval notation. Well, remember that this quantity x is represented by negative b over 2a. So when you find 4, it doesn't mean that the number of automobiles produced is 4. You were given the information that you were given X thousand automobiles. So if X is the number of thousands of automobiles and you found that X was 4, well, that means that we're talking about 4,000 automobiles or cars, whatever you want to call them. Now, you were not asked to find the cost associated with this number of automobiles, so you don't need to worry about finding the y-coordinate of the vertex. Now, the domain and range on this one are a little bit different. Anytime you're talking about real-world applications, you have to consider negative values. As far as the domain is concerned, we're talking about X being the number of automobiles produced. Technically, we normally say that for a parabola, the domain is all real numbers, but I can't produce a negative number of cars. And if X represents a number of cars, it's going to have to be, at its very least, 0. It cannot be negative. So for the domain, we can say that yes, we can produce 0 cars, but we can't produce negative cars. And I guess technically you could go all the way up to infinity. We can't really put a cap on that, although we know they really can't manufacture an infinite number of cars.
Real life is so restrictive. You can't make negative cars or infinite cars.
I know, what's up with that? I do feel like we have a lot of limitations that we're dealing with here. Yes.
You can definitely owe people cars.
What's that?
You can owe people cars. Wouldn't that be a negative car?
That's true. You can, technically, but well, I guess like Elon Musk could be considered producing like negative cars because his wait lists are so long and people are still waiting for their cars. But he can't really like unmanufacture them. If that would be a representation of negative manufacturing, I don't know. But officially, we can't do it. Can't do it. So got to think about these things when we're talking about real world applications. As far as the range is concerned, we're talking about a minimum cost. And you know what? I just said that we don't need to talk about the cost, but actually we do. Because to talk about the range of the function, we need to find out what this smallest value is where our vertex is sitting. So yes, we are going to have to find this value for the range, f of 4. Was not thinking about that in advance. 4 times 4 squared minus 32 times 4 plus 128. Let's see, 64 minus, just put it in my calculator. 128 plus 128 is 64. Now, if you're like, okay, 64, fine, go back to the problem statement and make sure you know what 64 is. Remember that C of X represented a cost, and it was a cost in millions of dollars. So when you find this Y value, that's what corresponds to C of X. You know how Y is usually F of X. Same idea here, it's just C of X. It's still a function that's being evaluated at some independent variable X. So this is in millions of dollars, but who cares about the dollars part? We just care that it's in millions. So at the vertex, when we have this minimum value at X equals 4, we have a minimum value of Y at 64. But 64 million. Oh, and this is going to look complicated with that 0 there, or with that comma, I should say. Now, I guess the cost could officially, technically just keep going up, even though it's really not going to reach infinity. Such is life. That's your range. Oh gosh, I missed all this interesting stuff going on the chat. Oh, yes, Karen's, yeah, your cousin's in kindergarten, yep, upset. You know, and it's not even that the teacher never calls on them, like she does. It's just that she's got 22 kids and she can't just be calling on them all the time, you know? Yeah, it's really unfortunate. Michael is saying that a recall could represent negative cars. Maybe. But I guess that wouldn't necessarily go along with manufacturing the cars. Beth's siblings are in high school. The brother especially likes being able to play games. Yeah. See, at least the kindergartners are like really wanting to be involved, whereas like the other students are just like doing other things here, don't care about learning. Yeah, I know. It's sad. It's like I'm actually really happy that we have half-day kindergarten. It was sad before, but now it's great because there's so much crying that happens. It's just a lot of crying. Excessive amounts of crying. Okay, I lost this. Okay, so that was 3.1. I just want to briefly talk about what polynomials are in 3.2 before we get into the nitty-gritty here. We might as well just talk about some definitions that we can include here before you hit the weekend. All right, polynomial function. Nobody likes this definition. It sounds very complicated. I'm gonna try to give you just an easy synopsis. Let n be a non-negative integer. That's really important. I know that sometimes in these definitions we tend to skip over stuff like that, but that means that n has to be something like 0, 1, 2, 3, 4, 5, whole numbers, basically. Well, actually the whole numbers, yeah, whole numbers include 0. Sometimes you would have heard about these being called natural numbers. Well, natural numbers don't include 0. Either way, integers. So you're not talking about values like 1/2, 0.27, nothing like that. They have to be whole numbers. And then we're letting a sub n minus 1, a sub 2, a sub 1, a sub 0 be real numbers such that a sub n cannot equal 0. The function defined by f of x equals blah, 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 you can read it, is called a polynomial function of degree n. The number a sub n, the coefficient of the variable to the highest power, is called the leading coefficient. So we're going to do a lot of work here with the leading coefficient, especially as it pertains to the end behavior of your function. But for now, it's really important to note that you're going to have some sort of number, then a variable to a whole number power. If your power cannot be a half, that means your variable cannot be underneath a radical. Can't have that. It's not a polynomial. So you cannot have things like, I don't know, the square root of x, that would be 1. You can't have like x to the 2/3, which anything that can be written as a radical, something like this cannot be in the terms of your polynomial. And you cannot have variables in the denominator. So you can't have something like this, like 2/x or anything like that. So you can't have your variables inside radicals, you can't have your variables taken to rational powers, and you can't have variables in the denominator. Those are the big things that keep your function from being a polynomial function. So far, the polynomials that we've mostly focused on have been quadratic. So quadratic functions are polynomial functions of degree 2. Now, the degree is n. In your definition, your first term is x to the nth power. So a quadratic function has n equals 2. That's why it's a second degree polynomial. We're going to focus in this section on polynomials that can be of much larger degrees, like 3, 4, 5, 6, maybe 7. But they start getting really complex after a while, and we won't talk about them when they get that complex. So we're no longer restricting ourselves to having a lead coefficient that has a variable to the second power. So what we're going to do is we're going to use this definition to talk about whether the function is a polynomial function, and we'll answer the questions. F of x equals 2 minus x to the 5th over 3. Is f of x a polynomial function? It's kind of a trick question, but kind of not. What do you guys think? Polynomial function, yes or no? Nobody wants to say. bring you back to this crazy definition. Is it a polynomial function? Beth says yes. I just see her nodding. I can't see anyone else except I can barely see Daniel. It's very dark in there. But I'm really happy he still has his camera on regardless. Beth is right. It is a polynomial function. And some of you might be thinking, well, it's a fraction. How can it be a polynomial? Doesn't matter because the denominator doesn't contain any variables. And because of that, you can rewrite this if you really wanted to. Using that common denominator like this. And you still would have a polynomial function. You could even write it like that. Now it looks a little bit more polynomial-ish. Sorry, this looks like a 6 and I don't know why. You can write that in multiple ways and it looks more polynomial-ish now. So yes. And then I'll even write a note here. There are no variables in the denominator. That would make it a rational function, which we will talk about in like 2 weeks. Now the next question for B is, what is the leading coefficient? Don't say 2/3 because you have to have this written in descending order. That means that the powers on your variable should start in the first term with the highest power and then go downward. And you can see that happening here in the definition. You're starting with the highest powered exponent, and then you're just decreasing it by 1, and then eventually going down x to the second power, x to the first power, x to the 0 power, because the quantity to the 0 power is just 1. So the leading coefficient we can find by rewriting this one more time and switching the order of the terms as negative 1/3 x to the 5th plus 2/3. Keeping the signs that were originally attached to those terms. And now we can tell, oh, I was about to give away the answer to C. Let me reword this. Now we can see what the leading coefficient is because it is just the coefficient that's hooked on to your leading term. The leading term is the one with the highest power on it. So the leading coefficient is negative 1/3. And this, I should say, is in descending order. Because all of your powers are getting smaller. You only have 2 in this case, but they're going downward as you continue along your function. The degree of f of x is just the highest exponent that you see, which in this case is 5. So you're going to have some questions like this on your homework that are going to ask you, is it a polynomial? And then you're going to have some like options for yes or no. And then like the next question would say, if it's a polynomial, what's the lead coefficient? And you'll have 2 options. One of them will say the lead coefficient is, and the other one will say it's not a polynomial. So that's kind of how they're going to ask you that. For number 2, the function is 3 minus 3 over x squared. Is it a polynomial? What do we think? Polynomial? Michael says no. And Nancy says no. And they are correct because you cannot have variables in the denominator. This is a problem. So is it a polynomial function? You would say no because there is a variable in the denominator. If it's not a polynomial function, then you can't even talk about the lead coefficient. You can't even talk about the degree of the polynomial because it isn't one. Now let's read through these characteristics just so it's one less thing we have to do next time. To recognize characteristics of graphs of polynomial functions and determine the end behavior, we will refer to the following. Polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So you're not going to see a lot of sharp points. You're not going to see any sharp points. You're going to have a continuous graph. That means that you're going to be able to draw it without ever having to lift your pencil. You're going to spend a lot of time in calculus talking about continuous functions. Polynomials are continuous functions. You're going to draw them. They're going to be nice, smooth curves. You're never going to lift your pencil. So not like a piecewise function. By smooth, we mean the graphs contain only rounded curves with no sharp corners. By continuous, we mean the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. Now, when we get back into this next time, we're going to start by talking about end behavior. The end behavior of the graph of a function to the far left or the far right is called its end behavior. So basically what we're thinking about is, as x goes all the way to negative infinity and as x goes all the way to positive infinity, what is y doing in both cases? So if x is going all the way to the left, is y going down? Is it going up? Is it leveling out? Does it have a horizontal asymptote? That's one thing we'll talk about as we get into 3.5 and talk about rational functions. We're going to focus a lot on end behavior. It's a very important concept. Although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left or far to the right. So that means for polynomials, you're not going to have any sort of horizontal asymptote. That will not happen with a polynomial function. You'll see that with rational functions. The sign of the leading coefficient, a sub n, and the degree n of the polynomial function reveal its end behavior. And that is where we will pick up next time. I will have your tests graded before Monday. I have about 40% of them graded right now. I can't physically hand them back to you, but I'm grading them on D2L. So I'm going to have all the notes and whatever point losses are going to be on there. And then when I finish grading everybody's, I think this is how it works, that I'll hit the publish button and then it'll fill into the grade book. So because I'm paranoid and I haven't done this before, I have running a sheet of all the totals, but it seems to be working really well right now. So yes, your test will come back on Monday. I have some homework that will be available to you at 7:50. I'm just going to add a couple are these polynomials or not problems to it real quick so that you can get started on that. Otherwise, I'll be in my office hour for another 15 minutes. If you have questions, please stick around. And if not, I will see you Monday. Have a wonderful weekend.